Allie, did you know that you're my better half?
Well, you're really the apple of my eye.
Dang, you're on a roll.
You know, all this bread talk really makes me hungry for bread.
You know, I've always wondered about the chemistry of baking bread.
Well, let's shrink down to the size of a particle and really see what's going on between those molecules.
Maybe we should take this to the kitchen.
Okay.
Baking bread is a really good example of a few chemical reactions that take place in a myriad of baked goods.
The first step in making bread is creating the starter.
A starter is a combination of bacteria and wild yeast from the air that survives in a bubbly, sticky, and acidic mix.
The bacteria in the starter is lactic acid bacteria.
In a typical starter, lactic acid bacteria outnumber the yeast as much as 100 to 1.
Like certain yeast, lactic acid bacteria digest simple carbohydrates, but instead of the alcohol created by yeast, lactic acid bacteria mostly produce sour lactic acid as a byproduct.
The production of lactic acid lowers the pH to a total of 3.5.
This lowering of pH results in that sour flavor of sourdough.
A low pH eliminates unwanted pathogens like Enterobacteria or Staphylococcus.
So what I'm hearing is that microbial baddies can't survive in an acidic environment.
That's right, and it is the driving force behind lactic acid fermentation, which also occurs in our own muscles.
I'm kind of hungry. Let's get started.
Ready or not, here I come.
When we add yeast to the mixture, the sugar is fermented.
In doing so, it releases carbon dioxide gas.
I think my dad does that.
And this releasing of the gas is what makes the bread rise, and the sugar is converted into alcohol, further contributing to the flavor.
Next, we add the egg,
Half a cup of milk.
a half cup starter, and now we mix. Next, protein bonding takes place. This is when glycogen and glutenin
Two key proteins in the flour.
combine to form strands of gluten. Kneading allows these proteins to expand and the molecules to bond.
This allows for a more elastic and fluffy dough. Looks like this.
Right now, we're browning the butter.
Stop buttering me up.
Browning butter is a process of slowly adding heat to butter.
The color change is a result of chemical fusion, a process we often perform in the lab.
Fun fact, this is often called the Maillard reaction, and it was coined by a French chemist who is known for dissecting kidneys.
And buttering the pan is efficient because of the specific chemical structure of butter, which allows for a better grease.
This is because most butters are 80 to 82% milk fat.
Let's grease this pan up.
Butter now than never!
While we wait, let's do some experimentation.
In kitchen chemistry, it's crucial to know the basis of heating.
And not burning.
Right now, we're boiling some water. Let's graph it.
As you can see, this is a graph of the heating curve of water at 1 atm of pressure. The y-axis is a measurement of the temperature at degrees Celsius, and the x-axis is a measurement of the heat added.
The graph starts at negative 30 degrees Celsius, and this is ice. As the water is being heated as a solid, it turns into a liquid. Here's this plateau as intermolecular forces are being broken. Later, as a liquid, the water turns into a gas, being heated as a liquid, and there's a plateau of vaporization.
As you can see, the plateau of vaporization is much larger than the plateau of melting. This happens because it takes more energy to break more of the bonds at vaporization because these bonds being broken are hydrogen bonds. The bonds being broken at the melting are only London dispersion forces and dipole-dipole forces, which don't need as much energy to break.
Let's check on the bread now. Wow, it looks like it has doubled in size. Looks like it's time to gently roll out the dough.
Oh man, we have to wait another 30 minutes to let the dough rest.
It sure takes a long time for carbon dioxide gas to form within the dough.
Man, I'm thirsty.
Me too.
We should make some lemonade.
Great idea. Shh. She doesn't know that I'm gonna pull a scientific experiment on her.
Let's add some baking soda. My lemonade.
Here you go.
Oh my scrumdiddlyumptious! You just pulled a scientific experiment on me!
And you totally fell for it.
Did you know that when the acid of the lemonade, or the citric acid, it comes into contact with the carbonate base, or baking soda, a chemical reaction is formed?
This created a carbon dioxide gas. As you may know, carbon dioxide gas is the same gas that is used to give soda their fizz.
You know what?
What?
I'm really interested in acid and base chemistry, especially in beverages.
Really? Did you get a 9 out of 20 on that test?
No, that was you.
Oh, we really need a review then. Fundamental concepts of acid and base chemistry is the ionization of water. As two water molecules are approaching equilibrium, they produce hydronium and hydroxide. And then two vocab words are bronzolari base and a bronzolari acid. A base is someone who accepts a proton, and an acid is one that donates a proton. So as you can see here, this water molecule is donating a proton, so this would be the acid, and this water molecule is accepting a proton, so it would be a base. On the other side, the hydronium would be the conjugate acid, because it's accepted a proton, and the hydroxide would be the conjugate base, because it has donated a proton.
So this is the equilibrium expression for the autoionization of water. So to create an equilibrium expression, we would do products over reactants. So as you can see here, we have the aqueous products, which is a hydronium ion and a hydroxide ion. But since water is a liquid, before the autoionization of water, we don't include it in the equilibrium expression. And the W in the equilibrium expression purely means that this equilibrium expression is for water. And as you can see, we have the equation that at 25 degrees Celsius, the equilibrium expression of water is equal to 1 times 10 to the negative 14. So this is the pH scale. As the pH decreases, a solution becomes more acidic, but as the pH increases, it becomes more alkaline or basic. And so when a solution is more acidic, there's a higher concentration of hydronium ions, or H3O+, than there are hydroxide ions, or OH-. So when you have a higher concentration of hydroxide ions, that means the pH is going to be lower. But as we reach equilibrium, the hydroxide ions will equal the hydronium ions. And then as you become a more basic solution, there will be less hydronium ions than there are hydroxide ions.
There are a few key calculations to know about pH. Firstly, to go between the concentration of hydronium and the concentration of hydroxide, this is the calculation. It's the Kw is equal to both of the concentrations multiplied. To go between pH and pOH, it should be pH plus pOH is equal to 14, which is the midway point of both. And then to go between the concentration of hydronium and pH, you can take the negative log of the hydronium. And then P represents negative log for anything. So same for the other side. The pOH is equal to the negative log of hydroxide. You can manipulate both these calculations so that equals the concentration of OH or hydronium is equal to 10 to the negative pH.
Ready! Now it's time to take the bread out of the oven. Ooh. Ow! Go. This better not be crummy.
Take a bite, take a bite.
Can I guess?
Good?
Mmm.
Really?
Really good.
Wait, rate it on a scale from 1 to 10.
10, yeah.
Oh my god, that's really good!
Rated on a scale of 1 to 10.
12.
Whoa.
Well, it looks like we're done in the kitchen.
Let's head back.
Now that's all you need to know about kitchen chemistry.
Wow, chemists just seem to know all the solutions.
Now that's based.
Acid-based.